Moving slab heating in the inductor. The slab is moving in the inductor with a speed of 6 meters per minute. The task is to calculate the temperature distribution. I'm going to consider the cross-section of the slab. When the cross-section gets into inductor, the power generation starts. When the cross-section leaves the inductor, the power generation stops. So I'm going to replace the movement of this slab with the time variable power source. The power source parameter I'm going to calculate in AC magnetic problem, and the temperature I'm going to calculate in the transient heat transfer problem. Okay, let's start QuickField now. First, I need to simulate the AC magnetic problem and find out the power distribution. Here I have magnetic problem already prepared. You can check the video on the example page to see the step-by-step creation process. I will outline briefly the problem setup. It is the same inductor, but you take a look at it from the other side. In the model, you will see the inductor coil and the slab. Let's go back to QuickField. You can see the problem properties. The frequency is 150 Hz and the axial length is 1200 millimeters. Let's open the geometry model. This is the slab, and for the slab I provide magnetic and electric properties. And for the coil, I specify the current. As a result, I will get the power density distribution. Let's adjust the field picture. To take into account that the power distribution is not uniform, I'm going to divide the slab into several layers and calculate the average power loss in each layer. Then I'm going to use these values in thermal problem to calculate the temperature distribution. Okay, to divide the slab into layers, open the geometry model editor. Here I will draw the central line, switch to insert mode, and draw the line here. Switch to select mode, click the line to select, right click, duplicate selection, displacement up by 10 millimeters, and I need 5 copies more. Okay, let's zoom in. I believe I will have an extra line here, so click this line, duplicate selection by 5 millimeters. 1 copy. Okay, that's all. Let me check the label properties. Slab. Total current is 0. Conductors are connected in parallel. That's correct. So build the finite element mesh and solve the problem. Open the results. Let's zoom in. And here you can see the layers. Now let's use the contour tool and take a look at the power distribution along the slab. Click this edge to select and open the XY plot. This is the current density, change to joule heat power. This is the joule heat power density, watts per meter cube. As you can see, the power distribution along the slab is not uniform. I'm going to approximate this distribution with some function and then use this function to specify the heat source in thermal problem. The most simple way to approximate this is to use a square pulse, something like this. When the slab cross-section is here, the power generation is 0, and when the cross-section moves into inductor, the power generation starts. When the cross-section moves outside the inductor, the power generation stops. The total power produced by the layer, this is the area under this function, should be equal to the power produced by this pulse. This is the area under this pulse. So I need to find the total power produced in each layer. Okay, let's go back to QuickField. Close this. Contour, remove contour. Let's zoom in. Use the contour tool. Click inside the layer to select it. Integrals. This is the total power produced in this layer. Copy. Paste it here. Layer number 1. This is power. But I need to get the power in watts per meter cubed. I need to find the magnitude of this pulse. The pulse length is 600 millimeters, the length of the inductor. So to get watts per meter cubed, I need to divide by the pulse length, the axial length of the model, which is 1200 millimeters, and by the thickness of the layer. So the inductor length is 600 millimeters, the axial length is 1200 millimeters, and the thickness of this layer is 5 millimeters. So the power density is this value divided by this, divided by this, and divided by this. These are watts per meter cubed. I have 7 layers. Copy this, paste it here. This layer thickness is 5 millimeter, and these layers have thickness of 10 millimeters. Now let's calculate the power in these layers. Click the layer to select, click again to unselect, copy, paste, click to select, click to unselect, copy, paste, click, select, click to unselect, copy, paste, okay, we have got the power density produced in each layer on the inductor. Now let's proceed to the thermal problem. I create new problem, slab underscore thermal. Next, problem type is transient heat transfer, model class is plane parallel. The slab is very long, but I'm going to simulate only a cross section. Let's make the Z length to be 1 millimeter. Actually, this value doesn't affect the temperature distribution. It will affect only the integral values, such as heat flux. Okay, next. Next, I should specify the integration parameters. The slab speed is 6 meters per minute or 6,000 millimeters per minute, and the inductor length is 600 millimeters. So the cross-section will be in the inductor during 1/10 of the minute or during the 6 seconds. Then the cross-section leaves the inductor. Okay, let's make the simulation time to be 10 seconds and the time step to be 1 second. And the initial temperature is 900 degrees Celsius. Finish. In the geometry model, I should draw the cross-section of the slab. This one. So in QuickField, I insert a rectangle with the dimensions 1200 millimeters by 120 millimeters. Insert. And remember that the power distribution in the slab is not uniform, so I have divided the slab into layers. Let's insert a smaller rectangle with the dimensions 1190 by 110 millimeters. And another one. And another one. and another one, and yet another one, and the last one. Okay. For each layer, I assign the unique label. Zoom in, switch to Select Objects mode, click to select. This is layer 1, layer 2, layer 3, layer 4, 5, 6, and 7. And I should assign label to the boundary, to the surface of the slab. Hold the Ctrl button pressed to select multiple objects at the same time. Edges, surface. Now let's provide physical properties for these labels. Double-click the label name in the tree. Thermal conductivity of steel depends on the temperature. Here I have the dependency in the file, so I just copy this and paste it here. Okay. The density is 7,880 kilograms per meter cubed, and the specific heat depends on temperature. Here I have the dependency in the text file, just copy it and paste it here. Close. And the power in this layer is this value. Copy and paste it here. Remember, this power source is active only for 6 seconds, while this cross-section is passing through the inductor. So it is a pulse. I will use a built-in QuickField function. This function takes 3 arguments. Time, the built-in variable, then the pulse start, 0, and the pulse end, 6 seconds. Okay. And the same physical properties I should specify for all other layers, only the power source magnitude will be different. So I'm going to copy the label, paste it here, paste again, and then just rename them. This is number 2, number 3, number 4, number 5, number 6, number 7. Okay, let's correct the pulse magnitudes. Copy this value, paste it here. For the third layer, copy this value, paste it here. For the fourth layer, copy this value, paste it here. For the fifth layer, copy this value, paste it here. For the sixth layer, copy this value, paste it here. For the seventh layer, copy this value and paste it here. Okay. That's all for block labels. And remember, the slab is cooled by the air. The heated body radiates power. So for the surface, I specify the radiation boundary condition. The ambient air temperature is 20 degrees Celsius and the emissivity coefficient is 0.8. Okay. That's all. The geometry model and the physical properties are ready. Before I can run the analysis, I should build the fine element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Let's take a look at the results. Here you can see the temperature distribution in the slab after 6 seconds of heating and 4 seconds of soaking in the air. You can select the time layer This is 900 degrees Celsius initial temperature. And then see how the temperature changed in time. 6 seconds maximum value of the temperature, and then soaking for 4 seconds. You can build the temperature time plot for several points. Right-click any point and choose the time plot. And for this point, you will get the temperature distribution in time. I can select this point, time plot. This is the corner. This is the surface of the slab, some distance away from the corner. And this is in the center. 6 seconds of heating and 4 seconds of soaking. And if you need to simulate the process when the slab is passing through several inductors, you just add another pulse to the dependency. Here is the pulse. Copy. On our website in Downloads Free Tools section, you will find the formula plotter. Paste it here. The simulation time is 10 seconds. Display chart. This is the pulse. Starts at 0, ends at 6. And I will add another pulse, another inductor. We will have 6 seconds of heating, 4 seconds of soaking, and then another inductor. Second inductor starts heating at 10 seconds and finishes at 16 seconds. One pulse, another pulse. So I can copy this and paste it here in QuickField. And I should do this for other pulses as well. And remember to change the simulation time. 20 seconds. Okay, run the analysis. Open the results. Let's zoom in and take a look at the time plot. Heating, soaking, heating, soaking. So this way you can simulate the slab moving through multiple inductors. If you search for the moving slab heating in the inductor on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.